So here's that idea of water being in 3 different states. In a solid, water is interesting because as a solid, it gets less dense. That's weird. Most things don't do that, but water does, and it's because of its chemical nature, the shape of the molecule and the way it arranges itself when it gets cold. But you notice that the liquid, the solid, it's not so much the space, but it's the rigidity of how they're held together. The organization, yeah. In the liquid, those molecules are free to move around on one another. In the solid here, they're not. That is similar to all other matter. In a liquid, the molecules can roll and move around on one another. In a gas, they're not even touching each other for the most part. Okay? A chemical property is a property that's related to the changes that a substance undergoes when exposed to different substances. So how do things react with one another? Quite often a chemical change is associated with a chemical reaction. So when a chemical reaction occurs, we divide things into two categories, or either reactants or products. The reactants are the substances that go into the chemical reaction. The products are the substances that come out. So if we had an example of reaction, carbon and oxygen forming carbon dioxide, the carbon and the oxygen individually would be the reactants, and the carbon dioxide would be the product. That should also be review, right? Okay. The evidence of a chemical change, when do you know a chemical change has occurred? If you see a color change, if you see a solid form from two liquids, if you see gases being produced when you mix two solutions, if you see the color change when you mix two solutions, if you see light being formed or heat being released, or even electricity being produced, that would be a sign of a chemical change. And then that last one, an indicator, an acid-base indicator changing color is evidence of a chemical change. Okay. So really what we're talking about here is when chemical changes occur, we're really seeing a change in energy. And a really easy way to demonstrate this is by adding electricity to water. What is electricity? What do we use it for? Energy, right? It powers our cell phones. It powers our lights and cars and all kinds of things now, right? It's energy. It's a nice, useful form of energy. When we add that energy, that type of energy to water, we can actually break the bonds in the water molecule and produce pure oxygen and pure hydrogen. And those two substances differ in their composition from water. And that was controlled by the addition of energy, right? So chemistry really is the addition and subtraction of energy. So energy is always involved when physical or chemical changes occur in the form of heat, light, and even electricity. But just like matter can neither be created nor destroyed, right? Energy can never be created or destroyed either. So we classify matter into some different categories: mixtures versus pure substances. Mixtures can either be homogeneous or heterogeneous, and pure substances can either be compounds or elements. Elements can't be further subdivided, as we said before. Compounds could be, but if left alone, they'll stay rather pure. They can still be considered a pure substance, even though they're not an element. Okay? A mixture, a homogeneous mixture. You may have seen that word before on the milk carton. Homogenized, pasteurized milk, right? All homogenized means, back, when your grandparents were kids, when they got milk delivered to their doorstep, that they came in a milk bottle, which had a neck at the top that got real narrow and then opened up again. The reason the bottle was shaped that way is because cream would float to the top out of the milk and would collect in that little cup at the top. Then when they brought the milk inside, they'd pour the cream off without having to pour the milk out. Then they'd put it back and they have their jar of milk. So they have cream and milk every day, right? What we do nowadays to the milk, though, is we homogenize it. And what that means is that it's blended up so much that the cream will no longer come out of the milk anymore. That's a homogenized solution. Does that make sense? Okay. And what homogenized means, or homogeneous means, is that it's all equal throughout the entire liquid, okay, or throughout the entire mixture. Okay, it's homogeneous. Heterogeneous means it would be different in different parts of the solution. So every sample of the solution you took, you'd get different composition. Does that make sense? So muddy water. You can imagine sampling muddy water. You might get a lot of mud in one sample and a little bit of mud in another sample, right? That would be a heterogeneous mixture. Another, I think this is pretty self-explanatory here, classifying elements, compounds, okay? So a mixture is a blend of two or more kinds of matter. Homogeneous, uniform in composition. Heterogeneous, not uniform. Pure substances have a fixed composition. It won't change, okay? Pure substances differ from a mixture in that every single sample of a pure substance will have the same characteristic properties. And every sample of a pure substance has exactly the same composition. Okay? For instance, water is always, all water, 11.2% hydrogen and 88.8% oxygen. That never changes with water. There are different levels of purity, and we'll probably be working somewhere around with substances somewhere around the middle of there. The more pure you get, the more expensive it gets. The quality of the chemicals we will be working with will be somewhere in the middle. Now, last thing, the periodic table. Hopefully you've all studied the periodic table before, so I'll go through this kind of quickly. But vertical columns are called groups or families, right? And horizontal rows are called periods. And we have three basic types of elements on the periodic table. You have metals, usually good conductors. They are solid at room temperature, malleable and ductile. You have nonmetals, which are usually poor conductors of heat and electricity. They are usually gases. If they're solid, they're brittle, and they are very poor conductors of heat and electricity. Nonmetals are, for example, are carbon, sulfur, phosphorus. Okay? And then sort of in the middle of the two, between metals and nonmetals, are something called metalloids. And they'll have characteristics of both. Sometimes they'll be brittle, but they will conduct electricity. Sometimes they're solid at room temperature, but sometimes their boiling point is low. They're kind of in the middle. Does that make sense? Okay. And then one last group worth mentioning is the noble gases. And they are in group 18. The noble gases are called the noble gases because they're pretty much unreactive. They noble in the idea that they don't react with all the other elements. So this is sort of comes from the old school, I guess you could call it, of the 1800s. Nobles very rarely interacted with the masses, so that's what they're kind of going at here. Noble gases in that they don't react with all the other elements. Okay.